Dear students, welcome to one shot series, and you must have seen schedule that this one shot series is in English. Crash course was in Hindi, you can say Hinglish, and these lectures will be in English. So in this today's one shot, we are going to discuss material science. Of course, material science is a big subject, and usually I teach approximately 35 hours to cover the entire syllabus of all the competitive examinations. But here for GATE 2023 and whatever is the upcoming exam, I thought of touching some key points, getting into the fundamentals, solving some important problems so that you are ready to face exam, because you people may not have time to go through the entire course. So that is the motto of this one shot series. So today is the first lecture of material science. These are my credentials. I am gold medalist in BTech because I was university topper from Aligarh Muslim University, and it is one of the prominent university in northern India. I did my MTech and PhD from IIT Delhi, and between MTech and PhD for 1.5 years I was IAS officer. I cracked both civil services mains and engineering services in year 1998. And last 23 years I am teaching different portions of mechanical engineering for competitive examinations. And I am also a researcher, and I am, as per Scopus data 2020, I am top 5% researcher in the world. Primarily I do research in the area of material characterization and metal forming. These are the areas in which I do research. This is our team. Because some people claim that they can teach everything and anything. That is not possible. See, I am a researcher. I say material characterization, finite element and metal forming. That is my area of research. I cannot say the thermodynamics, Clausius equations and all that. I cannot claim that I mastery in that. So here at PW we have team. They are expert in basically every subject. And we have, for mechanical, we have 12 members team. And me, I'm touching basically material science, production and industrial in different batches. So we are a team, okay na? And we are expert for every subjects, different teachers. So now let us discuss material science. I have few lectures on YouTube on the dislocation theory. So in those lectures, what I teach you, that alloys are always stronger than the pure material. Alloys are always stronger than the pure material. So these are the one shot series, so you have to be attentive for a long period of time. Alloys are always stronger than the pure material. And I have dismantled this information in my YouTube lectures. These lectures are available on YouTube. You can watch at any time. So I will give you some example. In India, every family purchase gold jewelry. Every family, most of the ladies and sometimes gents are also, they are attached to wearing gold. So 24 karat gold is 100% pure gold. 24 karat gold is 100% pure gold. Those who are experienced in purchasing gold, they may be knowing what I'm talking about. 24 karat gold is called 100% pure gold. But with 100% pure gold or 24 karat gold, you cannot make any jewelry out of it because material is too weak. Pure materials are very weak. Pure materials are very weak. They don't have a strength. Once again, my lectures on dislocation theory, please watch what I'm talking about now. So what we do, we add impurity. We add impurity to make the gold stronger. You must have seen in the jewelry shop that there is a 22 karat gold or 916. You know, the jewelry shop, they advertise a 916 gold. You know, what is this 916? What is this 916? 24 karat is 100%. 22 divided by 24 into 100 comes out to be 91.6%. That's how that equation comes out to be. So 22 karat gold will be 91.6% gold, and the remaining 8.4% there will be impurity. There will be impurity. Previously, approximately 10 or 12 years back, sometime back, jewelers used to add impurity of copper. Jewelers used to add impurity of copper, and it is a good impurity. Okay? But nowadays, you know, from last 10 or 12 years, they are adding impurity of cadmium. They are adding impurity of cadmium. You know why the impurities are added? Why the impurities are added? Because alloys are always stronger than the pure metal. Otherwise, we will not be able to make any jewelry out of it. If we don't add impurity, we will not be able to make any jewelry out of it. We will not be able to make any jewelry out of it. So we have to add impurity. Now, problem is cadmium is a radioactive. So there are two problems. If you add cadmium, it's a radioactive. So you must be seeing now that there are those who wear jewelry, cadmium jewelry, their neck there will be black thing. Finger ring, there will be black thing. It's a radioactive action of cadmium. If you don't wear, after some time it will go away. Second problem is it depletes. So cadmium jewelry, it will break after some time. So there is a benefit of jeweler and the government both, because government takes tax. So, but for the people who are wearing jewelry, cadmium is not a good impurity, copper is a good impurity. But why I am discussing this thing here? To tell you that alloys are always stronger than the pure metal. Alloys are always stronger than the pure metal. Alloys are always stronger than the pure metal. Okay? Pure materials, they don't have much application in industry. Pure materials, they do not have much applications in industries. Now, if there are alloys, we think of phase diagrams. We think of phase diagram. Let us say there are two materials, material A, and it is having melting point 800 degrees centigrade. We have two materials. I want to make alloy of two materials. Material A is having melting point of 800 degrees centigrade. And the material B is having melting point, let us say 350 degrees centigrade. Two pure materials. Now I want to combine these two materials and form alloy. I want to combine these two materials and form alloy. It can be any composition. It can be any composition. For example, 30% B, 70% A. It can be any composition. Now my question is, what will be the melting point of alloy? This is the most favorite interview question. This is the most favorite interview question. What will be the melting point of alloy? Will it be more than 800 degrees centigrade? Or less than 350 degrees centigrade? Or the melting point will be in between? Whether it will be more than 800 or less than 350 or in between 350 and to 800 degrees centigrade. Generally, most of the students, you know what they answer? What they answer? Because alloys are stronger than the pure material, so the same logic they apply here. Sir, the melting point will be more than 800 degrees centigrade. Melting point will be more than 800 degrees centigrade. But that answer is wrong. But the answer is wrong. Always remember, this melting point and strength, this melting point and strength are two distinct properties. Melting point and strength are two distinct properties. They do not have any relationship. They do not have any relationships. You know what is the answer of melting point of alloy? It will never be more than 800 degrees centigrade. Melting point will never be more than 800 degrees centigrade. It will be either between 350 to 800 degrees centigrade, either between 300 to 800 degrees centigrade, or less than 350 degrees centigrade. Either the melting point will be in between or less than 350 degrees centigrade. It will never be more than 800 degrees centigrade. Now, question comes, who will tell me what is the melting point of that alloy? Who will tell me that what is the melting point of that alloy? Phase diagram will tell. Phase diagram will tell. So whatever I have discussed in the last 10 minutes, I have given you the background of the phase diagram. I have given you the background of phase diagram. Okay? Background of phase diagram. So now, in this one shot course, I am going to cover only the binary phase diagram. I am going to cover only the binary phase diagrams. There are different types of phase diagrams: unary phase diagram, binary phase diagram, and ternary phase diagram. But in the one shot course, I am going to discuss only the binary phase diagram. Binary phase diagram means when the number of components are 2. When the number of components are 2. Number of components are 2. Now, binary phase diagrams are plotted at a particular pressure. Pressure is constant. Pressure is constant. Binary phase diagrams are plotted at a particular pressure. Pressure is constant. But pressure is one of the degrees of freedom. Pressure is one of the degrees of freedom. So what is the Gibbs phase rule? C plus 2 is equals to F plus P. C plus 2 is equals to F plus P. C is the number of components, F is the degrees of freedom, and P is the number of phases. P is the number of phases. Now, phase diagrams are plotted at a particular pressure, but pressure is one of the degrees of freedom. So, available degrees of freedom is one less. Let us say there are F number of degrees of freedom in any thermodynamic system or metallurgical system. Now, 1 degree of freedom you have purposefully restricted. 1 degree of freedom you have purposefully restricted. So, available degrees of freedom are 1 less. Correct, na? So, what you do? Subtract 1 from both the side. Subtract 1 from both the side. Let us say this F minus 1 is a F star. F star is the available degrees of freedom. F star is the available degrees of freedom. So my equation will be C plus 1 is equals to F star plus P. So this is the modified Gibbs phase rule for binary phase diagram. Kindly do not put this formula in the calculation of any of the unknown parameter. For binary phase diagram, this is the formula we will be using. Please remember that. Why? Because available degrees of freedom are 1 less. Because available degrees of freedom are 1 less. Now this binary phase diagrams are of 3 types. If it is a live session, it is really, we got to do a lot of things in the live session because I can answer the questions and queries of the students. But still we have a PW Telegram channel. Through that you can direct all the questions to me. Okay, na? But if it is live, it's a totally different mechanism between us and the student. Okay, that's a recorded version. Okay. So binary phase diagrams are of 3 types. Binary phase diagrams are of 3 types. First is the isomorphism. First is isomorphism. What is isomorphism? Let us say we have a material A. We have material A. In this material, I am adding impurity of B. B is the impurity. See very, very carefully, because my experience of last 23 years of teaching is that unless and until you are from IITs, you do not know material science. Or up to certain extent you can say bits, because bits also teaching is very good. So unless until you are from these 2 institutions, your material science, you don't know anything. So please see carefully. There is a material A and I am adding impurity of B. Now there are 2 options. This impurity atom forms bond with the parent metal. This impurity atom forms bond with the parent metal and becomes part of it. Forms bond with the parent metal and becomes part of it. These things are called alloys. These things are called alloys. Impurity atom forms bond and becomes a part of the entire system. It's called alloy. But another possibility is there. Another possibility is there that when you are adding impurity atom, what this impurity atom will do, it will combine with few parent atoms. Impurity atoms will combine with few parent metal atoms and forms a distinct compound, and that is having properties altogether different than the parent metal or the impurity atom. And these things are called compounds. Alloys and compounds. Once again, what is a compound? When the impurity atom, after combining with few atoms of parent metal, they forms a distinct material, and this distinct material properties are altogether different than the parent metal and the impurity atom. This is called parent metal and the impurity atom. It is called compound and it is called alloy. Alloy means impurity atom forms bond and becomes a part of it. Now, if the impurity atom is forming alloys, again there are two options. When the impurity atom, see this part very, very carefully, because it's a one shot recorded, so I don't know how people are seeing, because if it's a live I can answer the queries. So that is the reason I'm getting into the background first before getting into the actual phase diagram. Alloys will be divided into two major categories. Of course, there are many categories, but two major categories. When the impurity atoms form bond in such a way, that it's a single phase. Same definition of phase: physically distinct, chemically inhomogeneous, and mechanically separable state of matter. Mechanically separable state of matter is called a phase. So if it forms a single phase, such phase diagrams are called isomorphism. And it is also called solid solution. Meaning when the impurity atom merges with the parent metal in such a way that the resulting microstructure is a single phase, it is called solid solution. See, based on that, in GATE also some question comes, na? And when that question comes, people keep on opening different books, and we don't get the answer in different book. Then they keep on looking at the solution of other teachers. All confusions. I think 2 years back, there was a GATE question, na? Like this. It's a GATE question. A, B, C, D, and in this region it was a single phase alpha. B is in the two phase region. So question was that at which point there will be solid solution. It's a gate question. At which point there will be solid solution. So naturally at point C, because this region is a single phase, so C will be the point of solid solution. It's a gate question. 1 or 2 years back, you just check the P by Q. P by Q also I am going to record, so it's a P by Q. Okay. So these type of questions appears in gate, but people don't know head and tail out of it. That's the reason I'm starting from the basics. Okay, na? So when the impurity atom combines the parent metal atoms in such a way that the resulting microstructure is a single phase. Resulting microstructure is a single phase. It is called solid solution or isomorphism. This as isomorphism. Okay. But suppose impurity atom after combining produces a phase mixture. Phase mixture means it will be more than one phase. Then it is not a solid solution. So when the impurity atom is combined, there are two options. Either there will be phase mixture or there will be solid solution. Correct, na? So now binary phase diagrams are of three types. Binary phase diagrams are of three types. Now we are discussing the classification of binary phase diagrams. Binary phase diagrams are of three types. First is isomorphism. Isomorphism means in the liquid state as well as in the solid state, it will be a single phase. Both in the liquid as well as in the solid state, it will be a single phase. Okay. The most important example for competitive examinations, most important example is copper nickel phase diagram. Most important example is a copper nickel phase diagram. So percentage of nickel increases in this direction, and the temperature is on the y-axis. Very, very important phase diagram. Copper nickel phase diagram is there are three very, very important phase diagrams for all the competitive examinations, including engineering services, GATE, PSCs. So all the three diagrams we are going to discuss today in this one shot. So on this axis it will be 100% copper, and on this axis it will be 100% nickel. 100% copper, 100% nickel. Okay. The melting point of copper is 1085 degrees centigrade. Melting point of pure copper is 1085 degrees centigrade. And the melting point of pure nickel is 1452 degrees centigrade. Is 1452 degrees centigrade. Okay. And the diagram appears like this. I'm sure for qualifying your B.Tech, you must have studied this diagram. I'm 100% sure. Here is a liquid. This is the solid. Okay, na? and in between it is a mixture of liquid and solid. It is a mixture of liquid and solid, and this region is called meshy zone. Meshy zone, two-phase mixture meshy zone. The line that separates the liquid phase with the meshy zone is called liquidus, and the line that separates the meshy zone with the solid phase is called solidus. So now this is the isomorphism phase diagram or binary phase diagram of type 1. Binary phase diagram of type 1. Let us say we have an alloy with CO percentage nickel. We have an alloy with CO percentage nickel, meaning 100 minus CO percentage copper, 100 minus CO percentage copper. So when we are heating, like in the pure metal, we said that the melting point is fixed, na? Pure copper, the melting point is 1085 degrees centigrade. Pure nickel, the melting point is 52 degrees centigrade. We can say that. But for alloys, we cannot say like this. For alloys, melting point is not fixed. If there is a meshy zone, melting point will not be fixed. There will be a range of temperature. At which liquefations and solidifications are taking place. There will be a range of temperature at which liquefations and solidifications are taking place. So as we are heating it, this is the temperature at which the liquefaction starts. Upon heating, this will be the temperature. At which 100% material will be converted into the liquid phase. So T minimum to T maximum, that is the temperature range at which the liquefaction and the solidifications are taking place. Range of temperature during which liquefations and solidifications are taking place. Okay? Very, very important, because most of you may be studying the material science for the first time. So you have to see very, very carefully. Now, let us say same sample I am taking, CO percentage nickel and 100 minus CO percentage copper. I am taking the sample to a temperature. At which entire material is in the liquid phase. And from there, I am slowly cooling. Correct? And I would like to see the development of microstructure. Let us say this is the point A, point B, point C, and point D. So I have taken the sample to a temperature at which material is in the liquid state. From there, I am slowly cooling. Very, very important, slowly cooling. And I am seeing that how the microstructure is developing. So at point A, entire material is in the liquid phase. At point A, because it is in the liquid region, entire material is in the liquid state. Because the point A is above the liquidus line, so entire material will be in the liquid phase. So there is no question of any complications. I am cooling slowly. I am cooling slowly. So when you slowly cool to a temperature at point B, now we are in the mushy zone. Point B, we are in the mushy zone. So what will happen? At different places, solid start nucleating. At different places, solid start nucleating, and the rest is liquid. So because we are in the mushy zone, what is the mushy zone? Suppose this room, most of the places it is liquid, but some places it's a solid. Same thing. Mushy zone means some places there are solid nucleating, and rest of the place it is liquid. Okay? So this is the microstructure at point B. This is the microstructure at point B. Is that all right? Because there are many things in the diagram, so I will to make a fresh diagram. So these things are clear to all of you, especially when the lecture is going recorded. Now at this point, point B, these are liquid, these are solid, and remaining places it is a liquid. So this B point is, let us say, here. Draw a horizontal line. And this is called fulcrum. And this line is called tie line. Tie line. So this horizontal line, wherever it is touching the solidus line, this is a solidus line. So if you project it on the x-axis, let us say that percentage is CS. B point microstructure we have seen. Okay. And then this horizontal line, wherever it is touching the liquidus, you project it. This is CL. L means liquid, S means solid. You know what is the meaning of that? This liquid will have Cl percentage nickel, and the solid will have CS percentage nickel. See, all the percentage of nickel in the sample, is going to remain same. But it is divided between solid and liquid. Alright, nickel cannot come from anywhere, and also cannot go anywhere. but the CO percentage nickel is divided between the solid and liquid. So the same microstructure we have seen on the previous slide. Let us say ml is the mass fraction of liquid phase. Mass fraction of liquid phase, and ms is the mass fraction of solid phase. You know what I mean, that what is the mass fraction? Suppose there is a glass water, and this is ice. 30% ice, 70% water. Okay. So mass fraction of liquid will be 0.7, mass fraction of solid will be 0.3. That is the meaning of mass fraction. Because some students say that, because why I am taking such example? Because in the offline and the live classes, I have seen some student asking these type of doubts. Because there are three types of students. One are brilliant, means they will understand everything in one go and carry forward. Second is average. Third is a below average. And my 23 years of teaching experience in coaching setup, in every class, 60% students are below average. 60% students are below average. So why they are joining coaching? Because they want to improve their level. So increasing the level. So for them, I'm discussing these type of doubts, but ultimately, everybody has to increase the level. Everybody has to increase the level, otherwise selection will not come. Everybody has to increase the level, otherwise you will not get selection. Unfortunately, there are some coaching institutes and some teachers, they take advantage of this ignorance of students. So they will never teach funda. They will teach whatever the below average people can digest. Initially, it looks good, but such students will never be selected anywhere. So it's a cheating on part of teachers. So here, actually, what I do, everybody must increase the level of their fundamentals. Then I promise you, once the fundamentals are done, you will crack each and every exam. So why I have taken? Because some students are not able to understand, sir, what is the mass fraction. Okay, na? Once again, nickel cannot come from anywhere, and also nickel cannot go anywhere. So overall percentage of nickel is going to be same. So ms plus ml will be equal to 1. Correct, na? What is the proportion of nickel in the solid? ms and cs. cs is the percentage of nickel in the solid multiplied by mass fraction. It is the amount of nickel in solid. This is amount of nickel in solid plus mlcl, this amount of nickel in liquid, should be equal to CO. Two equations, two unknown. Because it's a recorded, but still I will give you some few seconds break so that you can solve on your own. So in the one shot also, you should have calculator and pen with you. Can you solve these two equations? I'm looking for value of ms and ml. ms and ml. ms and ml. So because I am going to do some work dot problems also, so some small breaks I will give you, 30 seconds maximum 1 minute, so that you can do the calculations. So ms is, if you solve these two equations, this is the CO minus CL divided by CS minus CL. ML will be CS minus CO divided by CS minus CL. This is the proof of lever rule. Proof of lever rule. Proof of lever rule. Okay. So you know how exactly it works. Lever rule can be applied only in the two-phase region. Lever rule can be applied only in the two-phase region. Single phase region and three-phase regions we cannot apply lever rule. And this side it is solid, this side it is liquid. We take the opposite side. We take the opposite side. Suppose I want to calculate the mass fraction of solid. Suppose I want to calculate the mass fraction of solid, I take the opposite side, means this divided by the whole thing. And if I want to calculate the mass fraction of liquid, liquid is on this side, take the opposite side. This divided by the whole thing. See, that's what I have done it. But if you solve these two equations, you are going to get the same thing. If you are going to use the solve the same those two equations, you are going to get exactly the same thing. Is that okay with everyone? Okay, na? So I have done the proof of lever rule. Proof of lever rule. I am discussing the development of microstructure. I have taken the sample to a temperature at which entire sample is in the liquid state, and then I am cooling slowly. So A, B. In the mushy zone, if you cool the material from B to C, if you cool the material from B to C, from B to C, naturally mass fraction of solid phase will increase. Mass fraction of solid phase will increase. So let us say these are solid phases. Solid and this is the liquid. Because when the solid is nucleating, as the temperature decreases, there will be growth. There will be growth. There will be growth. So C is the temperature. C is the temperature just above the solid S line. C is the temperature just above the solid S line. And D is the temperature just below the solid S line. D is the temperature just below the solid S line. So what will happen when the temperature is decreases from C to D? What will happen when the temperature decreases from C to D? Now this point is very important point. This point is a very important point. So when the nucleus of solid is formed, it is growing. Solidification front is growing. One growth, second growth, third growth. It is called one solid nucleus or solidification front. When the nucleus is growing, it is called solidification front. I hope all of you are attentive. Once again, we have to develop fundamentals. Without fundamentals, no question of selection. And we have to work hard. Each solidification front, atoms will be oriented in a certain fashion. Like here, atoms are arranged like this. This solidification front, atoms are arranged like this. And here, let us say atoms may be arranged like this. Each solidification front, there will be particular orientation of atoms. So when temperature of the sample decreases from C to D, temperature D is below solidus. So different solidification front will fuse together. Different solidification fronts will fuse together. And the entire sample will be converted into the solid phase. Okay, na? So the microstructure will be like this at point D. Microstructure will be like this. The regions at point D, all different solidification fronts will fuse together, and the entire sample will be converted into the solid phase. So the regions where different solidification fronts are fusing, there will be mismatch in the orientation of atoms. Atoms are oriented in this way, and these atoms are oriented in this way. This theta is called mismatch angle. So the regions where different solidification fronts are fusing, there will be mismatch in the orientation of atoms, and these regions of orientation mismatch are called grain boundaries. These regions of orientation mismatch are called grain boundaries. Understood how the grain boundaries are formed? There are different methods by which the grain boundaries are formed, but wherever there is a liquid to solid transactions, this is the mechanism of grain boundary formation. From solid to solid transaction, it will be a different mechanism of grain boundary formation. So very, very important concept of the grain boundary formation in materials. Very, very important concept of grain boundary formation in the materials. A very important concept of grain boundary formation in the materials. Now, question comes to our mind, and it's one of the favorite question in interview. Grain boundaries are good or bad? Grain boundaries are good or bad? Answer is depending upon the application you are looking for. Depending upon the application you are looking for. Grain boundaries are good as far as strength is concerned. As far as strength is concerned. Okay? Grain boundaries are bad when the corrosion is a criteria or creep resistance is a criteria. Creep resistance is a criteria or corrosion is a criteria. Grain boundaries are bad. See, at the grain boundaries, there is an orientation mismatch of atoms. There is an orientation mismatch of atoms. So because of this orientation mismatch, bond length will be large. At the grain boundary, because of orientation mismatch, bond length will be large. And larger is the bond length, easily bond can break. Larger is the bond length, easily bond can break. And that is the reason atmospheric oxygen first attacks the grain boundary atoms and the material will be corroded. First attacks the grain boundary atom and the material will be corroded. So more grain boundaries, more corrosion. So wherever corrosion is a criteria, we would like to minimize the grain boundaries. What is a creep? What is the definition of creep? Slow and progressive deformation of material over a period of time is called creep. Slow and progressive deformation of material over a period of time is called creep. Correct, na? So at high temperature, whenever I say high temperature, I mean the temperature above recrystallization temperature. Temperature above recrystallization temperature. So at high temperature, grain boundary material is having a tendency to flow. Grain boundary material is having a tendency to flow. So if there are grain boundaries, creep resistance will be very low. If there are grain boundaries, creep resistance will be very low. And where we require creep resistance? In aerospace applications. Aerospace applications like intercontinental ballistic missile. When there is a re-entry of missile into the Earth atmosphere, or let us say space shuttle. Space shuttle, whenever there is a re-entry of the vehicle, because of skin drag, temperature increases. And if the material creeps, the whole shuttle or ICBM is going to blast. So that material should not creep. You must have studied the Kalpana Chawla accident, very popular accident in the history of space exploration. The way we do it, in aerospace application, we use super alloys. We use single crystal super alloys. Single crystal super alloys. In the single crystal super alloy, there is no grain boundary. There is no grain boundary. The way we manufacture is, we take a seed crystal and by casting, we grow that crystal. In India, we have one government organization called Medhani. We have one government organization called Medhani. They manufacture super alloys for our aerospace needs. Aerospace needs by ISRO or DRDO, because intercontinental ballistic missile, any missile that has to go to the outer space, there must be super alloys, or space shuttle. So Medhani takes care of the needs of ISRO and DRDO. So very, very important organization as far as national importance is concerned. So manned space mission, the way we do it, there's a material. Over the material, we put small tiles of ceramic, because ceramics are very known to have very high creep resistance. So small tiles of ceramic, we cover the entire material. So during the takeoff, same space shuttle with other astronauts, Kalpana Chawla was also there. So during the takeoff, one of the small tile came out. And air traffic control knew that there is a small tile is coming out. But they cannot do anything because already launch is complete. So after the mission, when there was a re-entry of vehicle, so from wherever the tile came out, there was a creep, huge pressure difference, and the whole thing got exploded. So in such a crucial application, grain boundaries are bad, because grain boundaries are having a tendency to flow at elevated temperature. So till now, what we have discussed? We have discussed binary phase diagram of type 1. Till now, we have discussed binary phase diagram of type 1. And the type 1 phase diagram is isomorphism. Type 1 phase diagram is isomorphism. Now type 2, eutectic. Eutectic phase diagrams. And in the eutectic phase diagrams, the most important diagram is the diagram of lead and tin. Most important diagram is the diagram of lead and tin. During this one-shot series, if you face any difficulty, write in our PW Mechanical Telegram channel. All of you are having access to it. In this video below, there are some links to show how to join our respective Telegram groups. So all the support will be given from our side. So don't worry whether it's recorded or live. Live, of course, I can handle the doubts as it is appearing, but a recorded one, we don't know who is seeing what. But anyway, all support we will be giving you, okay? Na? So eutectic phase diagrams. So percentage 10 in this direction, temperature is on the y-axis. Now let us revise whatever I have discussed 1 hour before. Let us revise whatever I have discussed 1 hour before. When I am adding impurity material, how the compound will form and how the alloys will form. And when the alloys are formed, there are two conditions. One is isomorphism and the second is a phase mixture. So when the phase mixture is formed, alloy will follow this type of phase diagram. When the phase mixture is formed, alloy will follow this type of phase diagram, eutectic phase diagram. So on this axis it is 100% lead, and on this axis it is 100% tin. It is 100% tin, correct na? Melting point of lead is 327 degrees centigrade. Melting point of lead is 327 degrees centigrade. And the melting point of tin is 232 degrees centigrade. 232 degrees centigrade. Okay? And the diagram appears like this. This is the diagram. Alpha, beta, liquid. Alpha plus liquid, liquid plus beta, alpha plus beta. And 18%, 97%, 62%. In the phase diagrams, these temperatures and composition vary. These temperatures and composition vary from book to book, so don't get tension. Okay, na? Now here, this alpha phase is a solid solution. It is a solid solution of tin in lead. Solid solution of tin in lead. Beta phase is solid solution of lead in tin. Beta phase is the solid solution of lead in tin, but maximum 3% lead can be dissolved in tin completely at 182 degrees centigrade or 184 degrees centigrade. And alpha phase is maximum 18% solid solubility. So in other words you can say eutectics are partial solid solubility. Eutectics are partial solid solubility of one element into other. Partial solid solubility of one element into other. Okay? Is that okay, na? Now, whenever there is a partial solid solubility, partial solid solubility, on such phase diagrams, one reaction will appear. On such phase diagrams, one reaction will appear. One reaction will appear. This is approximately 184 degrees centigrade. See, at this point, what is happening? Liquid upon cooling is converting into two different solids, and it happens at 184 degrees centigrade and 62% in. So again, there is no mushy zone. There is no mushy zone, and this reaction is called eutectic reaction. This reaction is called eutectic reaction. Eutectic reactions are invariant in nature. Invariant nature means degrees of freedom are 0. Invariant means degrees of freedom are 0. So C plus 1 is equals to F plus P. Degrees of freedom are 0. C is 2. So P is equals to 3. You know what is the meaning? At eutectic point, three phases will be in equilibrium simultaneously. At eutectic point, three phases will be in equilibrium simultaneously, and it's a reversible reaction. Means if you heat, you will go on this side. If you cool, you will go on this side. Eutectic reaction. This is called eutectic temperature, and this is called eutectic composition. Invariant means that reaction will appear only at a particular temperature and a particular composition. Invariant means that reaction will appear at a particular temperature and a particular composition. That is called invariant. So eutectic, partial solid solubility and the limited solid solubility. So this is binary phase diagram of type 2. First category is isomorphism. Second category is a eutectic. Category 3 is a complete insolubility. Complete insolubility. Complete insolubility. I mean, the two materials, they are completely soluble in the liquid state, completely soluble in the liquid state, and completely insoluble in the solid state. So what kind of diagram it is going to come? What kind of phase diagram it is going to come? Like this. Liquid, percentage B, A plus B, liquid plus A, liquid plus B. See, in GATE exam, the reason I'm discussing, in GATE exam, already questions appeared, whatever I'm discussing, fundamentals. That is the reason I'm discussing. This type of diagram, only the alloys of bismuth, some alloys of bismuth follows this type of phase diagram. Some alloys of bismuth follows this type of phase diagram. So there are three types of binary phase diagram. There are three types of binary phase diagram. Now comes iron. Iron. Iron is a very important material. Iron is a very important material because whatever amount of material used in industry, 60 to 70% is iron. 60 to 70% it is iron. So, since ages, metallurgists were trying to identify how many faces iron has got. How many faces iron has got? How many faces iron has got? Metallurgically, as per material science, when we will consider that the material is undergoing a phase change. Suppose there is a solid metal, where by increasing the temperature or by any other means, when it is going to undergo phase change, how we will come to know? Either its crystal structure should change, or the size of unit cell should change. Size of unit cell is, let us say, this A. A is the size of unit cell. Crystal structure means BCC, FCC, hexagonal closed pack. These are different crystal structures. Either the crystal structure should change or the size of unit cell should change. Okay, na? How exactly we see the crystal structure and the size of unit cell? There are two equipments. By which we can know the crystal structure and the size of unit cell. These equipments are transmission electron microscope, transmission electron microscope, and the second one is X-ray diffraction. X-ray diffraction. That is the way we will come to know the crystal structure and or the size of unit cell. But imagine 100 years back, these machines were not available. 100 years back, these machines were not available. So how people knew that the material is undergoing a phase change? How the people knew that material is undergoing a phase change? Ultimately, why I am interested to know the phase change? Because if I know that there is a phase, I know the metallurgy of any material. If I know the metallurgy of any material, possibly I can tinker the material. See, in live classes, whenever there is an interaction, I will tell you many things. but I want to give you some idea here. See, there is one area of study called bioinformatics. There is something called bioinformatics. And if you see the countries like Singapore and other places, lot of money is being pumped. Lot of money is being pumped for the research of bioinformatics. I will tell you with what background bioinformatics research was triggered. I will tell you what is the background. Whenever we say science, one of the very important axiom of science is that whatever phenomena you are able to see in nature, it can be explained in the language of mathematics. Any phenomena you cannot explain in the language of mathematics, any phenomena whatsoever, if you cannot explain in the language of mathematics, that phenomena doesn't exist. This is as per science. Whatever phenomena you cannot explain as per mathematics, that phenomena doesn't exist. So bioinformatics is, we have heart, we have lungs, kidney, brain, we have so many organs and parts. I'm moving my hand. There must be some equation. That's what as per the science says. Mind, the way the mind is thinking. So if we can develop equations that relate the kidney, lungs, heart, mind, everything, if I can develop a relationship, possibly we can manipulate the relationship so that we can manipulate the body. This whole area is called bioinformatics. Anyway, this Terminator movie or this high sci-fi movies, Hollywood movies, they are based on this only. There's a program, everything, body is programmed. People are doing research, we don't know how much they will succeed, okay na? So if you know the metallurgy, possibly we can tinker the material. So these equipments were not available 100 years back. So how people knew that the material is undergoing a phase change? Temperature versus time. If you plot temperature versus time graph for water, if you plot the temperature versus time graph for water, it will be like this. Correct, na? Here there is a water and here is a steam. When we are heating water, at 100 degrees centigrade, although we keep on giving heat, but there is no increase in the temperature of water. Okay, na? And after some time it will convert into steam. This horizontal line tells you that there are latent heat transactions. There are latent heat transactions in the material. So around before this TEM and XRD machines were invented, idea was that in any material, if there are latent heat transactions, it means the phase change. That was the idea people were having. Same thing they applied for iron. Same thing they applied for iron. Same thing they applied for iron. Temperature versus time. Same thing they applied for iron. So what the metallurgist did, they have taken iron to a temperature. At which it was in the liquid state. From that temperature, they started cooling slowly. Cooling that too slowly. So it's a liquid iron. They are cooling slowly. First horizontal line appeared at 1535 degrees centigrade. So people understood that the liquid iron is converting into the solid phase. So latent heat transactions. Another horizontal line appeared at 1410 degrees centigrade. So people thought that iron is converting into another phase. Again there was a curve. Another horizontal line appears at 910 degrees centigrade. Another horizontal line appears at 910 degrees centigrade. Again there was a curve. Another horizontal line appeared at 768 degrees centigrade. And after that, there was no horizontal line. So what people thought at that time, 1, 2, 3, 4. What people thought at that time that there are 4 phases of iron. People thought at that time that there are 4 phases of iron, and they named it at alpha, beta, gamma, and delta. They named it like this. And this concept was there in the books for a long period of time. Later on, this TAM and XRD machines were invented. So what people found out that this is the BCC structure. This is also BCC structure. Neither there is a change in the crystal structure, nor there is a change in the size of unit cell. So how it can be a different phase? So later on, they removed beta. Up to 910, it is only alpha. This is FCC, and this is BCC. But BCC here and BCC here, there is a change in the size of unit cell. There is a change in the size of unit cell. So this is called allotrophy. This is called allotrophy of iron. What is the allotrophy? What is the allotrophy? When a material exists, what is the allotrophy? When a material exists in different phases at different temperature, material exists in different phases at different temperature, it is called allotrophy. So on this, we can see the three phases of iron: alpha, gamma, and delta. See, because it is a one-shot course and we are covering only the important topics for GATE 2023. So I will tell you here, there are 5 phases of iron: alpha, gamma, delta, Fe3C, and martensiite. Fe3C and martensiite we are going to discuss little later. Fe3C and martensiite we are going to discuss little later. And this characteristic of iron, due to which it exists in different phases at different temperature, is called allotrophy. And the purest form of carbon is called wrought iron. Purest form of carbon is called wrought iron. Roughly 0.00, let us say 6%. Roughly, I mean, percentage of carbon is very, very less. Now, I will tell you one story. Some of you may be in Delhi, or you might have visited Delhi. In Delhi, there is one place called Qutub Minar. And in the same premises as Qutub Minar, there is one iron pillar. There is one iron pillar. There is one iron pillar. Many historians say that this iron pillar is 1000 AD. 1000 AD, meaning at least 1000 or 1100 years old. This pillar is almost 1000 and 1100 years old. The specialty of this iron pillar is it is not corroding. It is not corroding. Why it doesn't corrode? Because it is made up of wrought iron. It is made up of wrought iron. The problem is, before year 2000, Y2K, before year 2000, India was not having technical know-how to produce IF steel. IF steel means 0.02% carbon. Interstitial free steel means 0.02% carbon. India was not having know-how to produce that material. Why the interstitial free steel or IF steel is important? Because car bodies are manufactured by this material. Car body, let us say your car cost is less than 10 lakh, like Maruti or Mahindra, Tata, less than 10 lakh. The car body material is IF steel. If the car is in the medium range up to, let us say, 30 to 40 lakhs, Fortuner, XUV, Tata, some variants are there, Sierra and all that, that material is a DP steel, dual face steel, DP steel. Up to, let us say, 40, 45 lakhs, up to Fortuner, you can say. But high-end cars, Mercedes, BMW, Audi, Rolls-Royce, generally their car bodies are titanium grade 5 material, titanium 6%, aluminum 4%, vanadium. So anyway, you know, if it is alive, we could have really enjoyed the material science like anything. Okay, but still let me know if there is anything. So before 2000, India was not having know-how to produce IF steel. But 1000 years back, how they produced this composition? 1000 years back, how they produced this composition? Still, it is a mystery. So even the metallurgists, they are not able to guess, because as per science, 1000 years back, Indian subcontinent were not having technology. At least they have their opinion. But how they could produce such a masterpiece if they don't have technology? Okay. So anyway, if you go to Delhi, please say this metallurgical marvel, iron pillar. So alpha, gamma, delta, Fe3C and martensite, there are 5 phases of iron. 5 phases of iron. Okay. All right. Next is, oh, okay, all right. Iron carbon phase diagram. Iron carbon phase diagram. This is the most important phase diagram, iron carbon phase diagram. This is the most important phase diagram. Percentage carbon on the x-axis. Temperature is on the y-axis. All of you, all the mechanical, XE, metallurgy, everybody should remember the iron carbon phase diagram. Whatever tricks I am telling you, if you follow those tricks, iron carbon diagram will be very, very easy to remember. Iron carbon diagram will be very, very easy to remember. Okay, na? So on allotropy, what are the temperatures we have seen? 910, 1410, 1535. See the sequence that I am going to follow. If you follow the same sequence, it will be easy for you. Do like this. And this, draw a horizontal line here. And this line appears at 725 degrees centigrade. 725 degrees centigrade, okay na? This also you make like this, same thing as here. See, follow the same sequence. It will be very, very easy for you. On iron carbon phase diagram, there are only 2 horizontal lines. On iron carbon phase diagram, there are only two horizontal lines. One is 725 degrees centigrade. Another is 1150 degrees centigrade. Okay. Now you do one thing. Fly 3 birds. So those who are watching the recorded lecture, some of you may be painters. So if you are painting, in the painting, how the bird flies? Like this. Birds are flying, na? Birds are flying like this. So fly 3 birds. First bird, you fly like this. First bird. I am flying 3 birds. Second bird, and third bird is flying upside down. Means birds flying upside down like this. So third bird is flying upside down. And join this like this. See, a diagram is over. Diagram is over. You have to remember the composition. Alpha, gamma, delta, liquid. This is the 6.67% carbon, and this is called Fe3C, cementite. This is 0.02%, 0.8%, 2.1%, 4.3%. Now apply 1-to-1 rule. This is the delta plus liquid, delta plus gamma, gamma plus liquid, liquid plus Fe3C, gamma plus Fe3C, alpha plus Fe3C, alpha plus gamma. This is your complete iron carbon phase diagram. Complete iron carbon phase diagram. On iron carbon phase diagram, 3 invariant reactions appears. 3 invariant reactions appears on iron carbon phase diagram. First reaction, eutectic. When the liquid upon cooling converting into gamma and Fe3C, and it appears at 1150 degrees centigrade and 4.3% carbon. See, the different books gives the different temperature and different composition. You should not worry about it. In exam, some hint will be given by which you will come to know that which temperature is which. Okay, na? This is the second invariant reaction. Gamma as a solid upon cooling is converting into 2 different solids, alpha plus Fe3C, second solid and third solid. One solid upon cooling converting into 2 different solid, it is called eutectoid reaction, and it is 725 degrees centigrade and 0.8% carbon. So there are three invariant reaction appears over iron carbon phase diagram. This is called eutectoid composition, and this is called eutectoid temperature. This is the third invariant point, peritectic point. Peritectic reaction. delta plus liquid upon cooling converts into third solid, and this temperature is 1493 degrees centigrade and 0.18% carbon. So iron carbon diagram is a diagram. Iron carbon diagram is a diagram at which three invariant reactions appear simultaneously at three: eutectic, eutectoid, and peritectic. There is some peritectoid reaction also, but peritectoid reaction doesn't appear on iron carbon system. Okay, so very, very important diagram, very, very important diagram. These materials are called steels up to 2.1%, and here it is called cast irons. Okay, so very, very technical details. This is the eutectoid temperature. It is called hypo eutectoid steels. This is called hyper eutectoid steels. This is called hypoeutectic cast iron, and these are called hypereutectic cast iron. Hypereutectic cast iron. So steels and cast irons, steels and cast irons, and there are further divisions. There are further divisions. In Latin, hypo means before and hyper means later. In Latin, hypo means before and hyper means later. Okay, so in last almost 2 hours, I have discussed some important phase diagrams, and it was really, all the information was quite compact. All the information was quite compact. Okay, now I want to take up some questions. And if there is any new fundamental, with the help of questions, I will be elaborating. So I will be little slow here. Because idea is that along with the course, you should also practice some problems. All right? I will give you full opportunity to read the question, and then if something is required, I will elaborate a little bit. The solidification of liquid at constant temperature into two-phase mixture is called there is no issue. It's one of the easiest question you can expect. We have discussed one of the easiest question you can expect. Eutectic reaction for iron carbon system occurs at Just now we have discussed these things. Don't actually, it's not a joke. These questions do appear in exams. So it's not a joke. Sometimes so that you can read it. Which is the isothermal reversible reaction? It is always a reversible reaction. Very, very important. It is always a reversible reaction, in which a solid phase is converted into two or more immediately mixed solids upon cooling. Solid phase is converting into a mixture of solid. Correct, na? Okay. If you see iron carbon diagram in steel range, iron carbon diagram in steel range, this eutectoid decomposition is called perlite. Perlite or pearl, Hyderabadi pearl, perlite. Perlite, the microstructure is, there are alternate layers of alpha and Fe3C. It's alpha and this is Fe3C. So perlite is a phase mixture of alpha and Fe3C, and it is produced by eutectoid decomposition. It is produced by eutectoid decomposition. Eutectoid decomposition. Perlite is not a phase. Perlite is not a phase. It's a phase mixture of ferrite and cementite. Perlite is not a phase. It's a phase mixture of ferrite and cementite. Okay. Yeah. Giving you 1 minute time so that you can read it. Giving you 1 minute time so that you can read the question. Because if it is a live, we could have taken a slightly different approach. But here I can give you some pause. In the lead and tin system, the fractions of total alpha phase is 3 times the fraction of beta phase. So lead and tin system, alpha beta. So what the question is telling you? The fraction of total alpha phase is 3 times the fraction of beta phase. So mass fraction of alpha is 3 times the mass fraction of beta. Okay? lead alpha phase is 90% in. Oh, change color will be better. 90% in and 2.5% lead. You know what is the meaning of that? It's a 19% in and this is 97.5%. So if you have a tie line, let us say this is X, and here is a fulcrum. So now you have to find out the composition X. You have to find out the composition X. So that is the question. Try. So the mass fraction of alpha, what I told you in this lecture, we take the opposite side. This divided by the whole thing. So 97.5 minus X divided by 97.5 minus 19. Mass fraction of beta is on this side, so we take opposite side. This divided by the whole thing. X minus 19 divided by 97.5 minus 19. M alpha and M beta put in this equation, you can get the value of X. Can you solve it giving you a pause of 30 seconds? Because it's a recorded lecture. If I directly give the answer, the purpose will be lost. Purpose will be lost. Okay, find out X. And this X will be percentage of 10. X will be percentage of 10. It's a 0.386. Okay. And the answer will come out to be B for Bombay. Answer will come out to be B for Bombay. All right. See the next problem. It is a multiple select question. I mean, more than one questions are correct. More than one questions are correct. More than one questions are correct. So in between every question, I am pausing for some time, giving you time to think. Because if I just show the question and giving you the answer, the purpose of this course will be lost. We will learn only when we contemplate certain things. Only then we will be able to learn. The correct statement. Characteristic of any series of alloy with one major element can be found by phase diagram. That is correct. You know why? Because we have studied the binary phase diagram. There is something called ternary phase diagram where there are two major along elements. So how the alloy will behave can be found with the phase diagram. So first statement is a correct statement. Phase diagram gives the information in which at any point percentage of phase present can be calculated, because that's what our lever rule gives. Our lever rule gives this only, na? So second statement is also correct. Second statement is also correct. See, the phase may be liquid or vapor with ordered crystal structure. Liquid and vapor have no crystal structure. Liquid and vapor, they do not have any crystal structure. So C statement is wrong. C statement is wrong. In phase diagrams, 1-to-1 rule can be applied. In phase diagrams, 1-to-1 rule can be applied. You know what is a 1-to-1 rule? What is 1-to-1 rule? This is the phase diagram. I am teaching you 1-to-1 rule. If I draw a horizontal line, on one side there is one phase, on the other side there is another phase. On one side there is one phase, other side there is another phase. In between it will be a mixture of this phase and this phase, means alpha plus liquid. This is called 1-to-1 rule. Draw inclined lines are not allowed. Horizontal line, so that it intersects any two lines. On one side there is one phase, another side there is another phase. In between it will be a mixture of these two phases. It is called 1-to-1 rule. So D is also correct. So A, B, D are correct statements. These are multiple select questions. This particular question is a multiple select question. Yeah. Giving you 30 seconds so that you can read. Then we will discuss. Consider the following statements in connection with the phase diagrams. Phase diagrams of binary alloy change by the presence of other alloying element. Binary phase diagram means one parent metal and another impurity metal. If I add another impurity material, binary phase diagrams will convert into ternary phase diagrams, so they will change. So first statement is 100% correct. First statement is 100% correct. You know, the way you should handle this one-shot course, after showing each question, I am giving you some pause. You do something, calculations or answers, and when I am explaining, you just verify. And if your answer is wrong, you learn. That's the best way to learn in the one-shot series. Tie line construction and the lever rule are used to determine the phase compositions. Correct. Tile and construction and lever rule are used to determine the phase composition. Ternary phase diagrams are three-dimensional diagrams. The way ternary diagrams are plotted is, there is an equilateral triangle. There is an equilateral triangle. Percentage A increases in this direction. Percentage B increases in this direction. Percentage C. And the temperature will be normal to it. Temperature will be normal to it. So, D will be the correct answer. D will be the correct answer. Read it. Consider the following statements in a binary phase diagram. The freezing point for the alloy is minimum for eutectic composition. This is the eutectic composition, and the melting point is minimum. Correct, na? So the moment we are deviating from the eutectic composition, melting point is varying. Melting point is varying. So it's a correct statement. Eutectic mixture solidifies at a constant temperature like pure metal. There is no meshy zone. So it behaves more or less like a pure metal. It behaves more or less like a pure metal. Eutectic reaction is irreversible. No, it is reversible. Reversible means if you cool this way, if you heat this way. So it is a reversible. At eutectic temperature, two liquids or two metals will be changed into two solids. So 1, 2, and 4 statements are correct. 1, 2, and 4 statements are correct. Read this question. I will wait for 1 minute. Read this question. It is a very good question. Purposefully, I am pausing for 30 seconds or so. Okay. You know what the question is telling you? For alloys are two hypothetical metals A and B, there exists an A-rich phase alpha and a B-rich phase beta. Meaning is, percentage of B, temperature, B-rich phase beta, A-rich phase alpha. That's what the question is telling you. Like a latent 10. Determine the composition of the phase boundary for both alpha and beta phases at this temperature. Okay, na? I hope you have studied the question properly. %weight A, because we have drawing in this way. 40 weight % V. So let us say we have tie line X. No, actually X and B, because this we have to calculate. X and Y. X is the solid solubility of B in A. Y is the solid solubility of A and B, that we have to calculate. Data given is 40 weight % of B. Suppose if it is a 40%, then fraction of alpha phase is 0.57. Alpha phase means take the opposite side, y minus 40 divided by y minus x. Okay. And the remaining balance will be 0.43 is a beta. So 40 minus x divided by y minus x. Correct? I hope, is that okay for you? Now take the second condition. What is the second condition? 70 weight % B, alpha is 0.14. Second condition is 70%. So mass fraction of alpha is nothing but y minus 70 divided by y minus x, and it is 0.14. And the second condition will be remaining balance is 0.86 is a beta. 70 minus x divided by y minus x. So you do one thing. It is a very good question. Do one thing. This and this you divide. 0.57 divided by 0.14 is equals to y minus x will cancel out. Y minus 40 divided by y minus 70. You have to find out y. And once you get y, you will get x. Once you get y, you will get x. Do it quickly. Y will be 79.8%. Put the value of y in any one of the equation. You will get x is 9.96%. So solid solubility of B in A is 9.96%, and solid solubility of A in B is 79.8%. Okay, it's an easy one. It was a very good question. It was a very good question. See this question. Once again, as I promised, I am giving you some time so that you can read. A hypothetical AB alloy of composition 55 weight% B. If you are focusing B, don't see A, otherwise it will lead to confusion. At the same temperature is found to consider the mass fraction of 0.5 for both alpha and beta phases. For both alpha and beta phases. These are very good questions. Alpha and beta. Okay, same type of diagram. So if it is a 55%, mass fraction of alpha and mass fraction of beta is same. So mass fraction of alpha is nothing but 55 minus x, 55. Oh, that's this data is also given to you, na? If the composition of beta phase is 90%, 90%, what is the composition of alpha phase? X we have to find out. 55 minus x divided by 90 minus x, and it is given as 0.5. Find out x. Okay, now these questions are easy. These questions are easy. And it will be 20%. It will be 20%. It will be 20%. Okay. Heat treatment. Heat treatment. The foundation of heat treatment is the TTT diagram. Foundation of heat treatment is TTT diagram. See, in iron carbon phase diagram, in the steel range, what we are able to see in steel range, what we are able to see that austenite is not stable below 725 degrees centigrade. In this region, you do not find any austenite. Correct, no? You do not find any austenite below 725 degrees centigrade. So, what exactly happened? There was one scientist, Professor Bain. There was one scientist, Professor Bain. He was conducting experiments. On steel samples having eutectoid composition. Eutectoid composition means 0.8% carbon. Eutectoid composition means 0.8% carbon. So what Professor Bain did, he took all the samples to 750 degrees centigrade. Once again, these are one-shot crash series. So I am covering only the important sections only. I am covering only the important sections, okay? So Professor Bain took all the samples to 750 degrees centigrade, and from this temperature he started quenching. Quenching means rapid cooling. Quenching means rapid cooling. He started quenching to different temperatures. And the temperatures were 700 degrees centigrade, 600 degrees centigrade, 550 degrees centigrade, 450 degrees centigrade, and 350 degrees centigrade. So he started quenching the samples of eutectoid composition from 750 to these different temperatures. And then what he did, after quenching, he was constructing a curve of time versus percentage decomposition. Time versus percentage decomposition. This is the 0% decomposition, and this is the 100% decomposition. He was constructing the curve between the time and the percentage decomposition. And these are the temperatures: 700, 600, 550, 450, and 350. What our iron carbon diagram says, that 725 degrees centigrade is the eutectoid temperature. 725 degrees centigrade is the eutectoid temperature, and below this temperature austenite is not stable. So percentage decomposition versus time. 0% decomposition, and this is 100% decomposition. Okay? So the first sample, when he quenched to 700 degrees centigrade, from austenite to 700 degrees centigrade, he quenched. Quenching means rapid cooling. What he found that for a considerable period of time, there was no change in the microstructure. It was austenite only. Upon quenching from 750 to 700 degrees centigrade, for a considerable period of time, there was no change in the microstructure. It was austenite only. So, this time period is called incubation time. This time period is called incubation time. This time period is called incubation time. So let us say for 700 degrees centigrade, decomposition started from here and finished like this. And this much time period is consumed in decomposition. Decomposition of austenite into some other microstructure. Decomposition of austenite into some other microstructure. So this graph is at 700 degrees centigrade. He took the second sample. And from 750 degrees centigrade, he quenched to 600. So what he found out, that there was decrease in the incubation time. Previously this much incubation time, now this is incubation time. And the sample took this much time to convert from austenite into some other microstructure. Third sample, from 750 he quenched to 550 degrees centigrade. Now what he found out, the decomposition started almost immediately, exactly after 1 second. It's a very, very important data. At 550 degrees centigrade, incubation period is only 1 second. Start, finish. Okay? Professor Bain took the fourth sample, and from 750 degrees centigrade, he quenched to 450. Now, when he was decreasing the quenching temperature further, what he observed, that incubation period started increasing again. And when the quenching temperature was 350, S5, F5, incubation period further increased. So what Professor Bain did, that he projected percentage decomposition versus time graph over temperature versus time graph. He projected percentage decomposition versus time graph over temperature versus time graph. So how to project? How to project? Constant temperature lines will be horizontal here. Constant temperature lines will be horizontal here. 725 degrees centigrade. So all these temperatures, $700, $600. All these temperatures lines will be horizontal. $550. $450. And $350. Now project 700. You project on the 700 line, S1, F1. Correct? No? That is the way we do project. 600. You project over the 600. $550 over $550. $450 over $450. And $350 over $350. Okay, I have projected, na? I have projected. Now join all S lines together, all S points together, and all F points together. Join all S points together and all F points together. This type of diagram appears. This diagram is called time temperature transformation curve. It is called time temperature transformation curve, or C curve, or S curve, or Baines curve. For a single diagram, there are 4 names. For a single diagram, there are 4 names, and that's how TTT diagram. That's how TTT diagram is constructed. That's how TTT diagram is constructed. It is very, very important to know how TTT diagram is constructed. Okay? All right. Correct? Now, there are 2 more lines on TTT diagram. Okay, na? There are 2 more lines on TTT diagram. Temperature versus time. This is called Martensiite start, and this is called Martensiite finish line. Remember from where we started. Remember from where we started. We are taking eutectoid composition. We are taking the eutectoid composition. This Martensiite start line is 220 degrees centigrade, and Martensiite finish line is 110 degrees centigrade. But kindly note that by change in the percentage of carbon, position of MS and MF line will change. By change in the percentage of carbon, position of MS and MF line will change. Okay? Now y-axis is temperature, x-axis is time. So if you draw any line on TTT diagram, the slope of that line will be the cooling rate. So from austenite region, if the cooling rates are such, that line just touches the nose of TTT diagram. Nose appears at 550 degrees centigrade and 1 second. And by the way, it's a logarithmic curve. Time is in the log scale. So when the cooling rates are such that the line just touches the nose of TTT diagram, it is called critical cooling rate. So any cooling rate equal to or greater than critical cooling rate, you will get Martensiite. This Martensiite is having body center tetragonal structure, and it's one of the most brittle phase of iron. Martensiite is the most brittle phase of iron. So if you see, this is the region of austenite, and when the cooling rate touches the MS line, austenite will begin to convert into Martensiite, and the moment this point is over, 100% austenite will convert into Martensiite. And when the cooling rates are slow, above the nose is the region of perlite, below the nose is the region of bainite, and here is the Martensiite. Properties of bainite always fall between perlite and Martensiite. Okay? When the cooling rates are very slow, cooling produces coarse structure. The reason is because of slow cooling, driving forces are not very high. So the microstructure develops very systematically. So very slow cooling produces coarse perlite, and when the cooling rates are faster and faster, you will get finer and fine perlite. Suppose my cooling rate is like this. then what microstructure I will get it here? 0% decomposition, 100% decomposition. If you plot 50% decomposition, so because the cooling rate is going from the middle, na? So at this point, 50% perlite and 50% austenite. You know why 50% perlite? Because the cooling curve is touching the 50% decomposition line. Cooling curve is touching the 50% decomposition line. And for TTD diagram, please remember one thing. For TTD diagram, please remember one thing. Once austenite convert into some other microstructure, it will never reconvert again. It will never reconvert again. So here 50% austenite is remaining. This 50% austenite will convert into martensiite. So here 50% perlite and 50% martensiite. So whatever is the remaining 50% austenite will convert into martensiite. So that's how the microstructure develops as per TTT diagram. Suppose you take a sample of austenite. You take a sample of austenite, and this sample you can quench into some medium. The medium can be water, oil, it can be different medium, but in the one shot I am not going to discuss that thing in detail. If you quench that into some medium, you may find that cracks may appear on the surface of quenched product. Cracks may appear on the surface of quenched product. Generally, when I ask in open class that why these cracks appeared, during quenching, students say thermal stresses. These cracks in quenching are not due to thermal stresses. These cracks in quenching are not due to thermal stresses. You know how these cracks appears? This is the surface and core. So any sample when you are quenching into some medium, surface and core may experience a different cooling rate. Surface and core may experience a different cooling rate. This is surface and this is core. Because, I hope everybody is hearing carefully, because surface comes in contact with the quenching medium, so immediately it converts into martensiite. But the core is austenite. See, this is the temperature, and at the same time this is the temperature of core. So core and surface are having a temperature gradient. Core and surface are having a temperature gradient. Core is gamma. Gamma is FCC structure. Martensites is body centered tetragonal structure. FCC structures are having highest atomic packing factor, so its density will be high, and martensite density will be low. Density depends upon the atomic packing factor. If the atomic packing factor is high, density of the material will be high. So because atoms are same, na, iron, but martensite and austenite has got different crystal structure, so density will be different. So austenite is having high density, martensite is having low density. So this is a sample. You quenched into some medium. Surface became martensite and became rigid. Surface becomes martensite and becomes rigid. But the core is still austenite, na? Having high density. Core is still austenite having high density. So after some time, when the austenite at the core converts into martensite, because ultimately everything has to come to room temperature. So core is presently austenite, and after some time when this austenite convert into martensite, material is going from high density to the low density. Material is going from high density to the low density. So core volume will expand. Core volume will expand. But surface is rigid. When the core volume expand, this will produce cracks over the surface. When the core volume expand, this will produce cracks over the surface. So suppose somebody ask you, na? Somebody ask you how the cracks appear during quenching. One line answer is due to density difference. Cracks during quenching appears due to density difference. Cracks during quenching are due to density difference. So in most of the quenching, cracks will appear. So how to avoid these cracks? The method is Marr tempering. Marr tempering is also called stepped quenching. Marr tempering is also called stepped quenching. So what we do, temperature versus time. What we do, initially the material is quenched into a hot medium. Initially the sample is quenched into a hot medium, maintained at a temperature below the nose but above martensite start line. Hot medium. Keep the sample in the hot medium for a certain period of time. Keep the sample in the hot bath for a certain period of time, so that the temperature of surface and core becomes uniform. After that, take out the sample from the hot bath and placed in the cold bath, maintained at room temperature. So Marr tempering is quenching in two medium. So by this two medium quenching, temperature gradient will decrease and decrease in temperature gradient. Decrease in temperature gradient will decrease the density gradient. Decrease in the temperature gradient will decrease the density gradient. So that is how we avoid cracks during quenching. See, there is a process called 𝐂𝐨𝐻 tempering. There is a process called 𝐂𝐨𝐻 tempering. What is 𝐂𝐨𝐻 tempering? What is 𝐂𝐨𝐻 tempering? Sample is initially quenched to a hot bath maintained at a temperature below the nose but above martensiite start line. Quench it in this range. Then this temperature is maintained. This temperature is maintained for a substantial period of time. So that the decomposition line enters into TTT diagram and you will get bainite. Only 𝐂𝐨𝐻 tempering will produce bainite. Only 𝐂𝐨𝐻 tempering will produce bainite. Bainite cannot be produced by continuous cooling. Only 𝐂𝐨𝐻 tempering will produce bainite, and bainite cannot be produced by continuous cooling. Bainite cannot be produced by continuous cooling. And suppose, now you should know how to tinker the microstructure. Suppose cooling rates are such, then what microstructure you will get it here? Here 50% bainite, 50% austenite. Because we are diverging now, so this austenite will convert into martensite. So 50% bainite and 50% martensite. Okay. So how to manipulate the TTT diagram? Okay, now that all of you should know. How to manipulate the TTT diagram? All of you should know. How to manipulate TTT diagram? All of you should know. Now, whenever I say heat treatment, when I say heat treatment, this heat treatment is having 4 categories. Annealing, normalizing, hardening, and tempering. Hardening and tempering. There is something called case hardening. Case hardening is called secondary heat treatment process. Secondary heat treatment process. So heat treatment, very, very important discussion of heat treatment. So look at the screen. Again, iron carbon diagram in steel range. Now, full annealing is of 4 types. Annealing is of 4 types. One is called full annealing. Second is called process annealing. Third one is called spherodise annealing. And fourth is a diffusion annealing. There are 4 types of annealing process. There are 4 types of annealing process. In between, I am giving you a small 30 second break so that you can the purpose of full annealing is to increase the toughness of the material. Toughness of the material. This temperature 725 degrees centigrade is called lower critical temperature. 910, this line called upper critical temperature. There is a reason, I don't want to get into the reason at this moment. These are hypo-eutectoid steels and these are hyper-eutectoid steels. So full annealing temperature range is this C. This is the temperature range of full annealing, meaning for hypo-eutectoid steel 50 degrees centigrade above upper critical temperature, and for hyper-eutectoid steels 50 degrees centigrade above the lower critical temperature. Now the samples are kept at this temperature and then cooled slowly in the furnace. The slow cooling means it is approximately 200 degrees centigrade per hour. Because of slow cooling, what will happen? You will get coarse grain structure. Because of slow cooling, what will happen? You will get coarse grain structure, and the coarse grain structures are tough. Coarse grain structures are tough. So resulting microstructure after full annealing is a coarse perlite. Okay. Now the process annealing, this is the temperature range. Process annealing is performed to remove the after effect of any process. Process annealing is performed to remove the after effect of any process. And what is the after effect of any process? Work hardening, dislocation pile up. Work hardening or dislocation pile up. So what we do? We heat the material to the recrystallization temperature of the material. We heat the material to recrystallization temperature, and the recrystallization temperature is approximately 0.5 times the melting point. Melting point of the material should be in the Kelvin. 0.5 times the melting point of the material. And when you are cooling slowly, due to the formation of newer crystals, dislocations will die out. So stress relieving. Process annealing is called stress relieving. This spherodise annealing is meant for medium carbon steel or high carbon steel? Spheroidized annealing is meant for medium carbon steel or high carbon steel? Because of high percentage of carbon, these materials are not machinable. So, spheroidized annealing is performed to increase the machinability of these materials, and this is the temperature range. The temperature range of spheroidized annealing. Heat up to this point, cool slowly in the furnace. Some of the students ask, and it's a very popular question, because let us say if it is live or it's an open class, question is, array sir, for high carbon steel, or you can say hyper-eutectoid steel, what is the difference between full annealing and spheroidized annealing? What is the difference between full annealing and spheroidized annealing? Difference is the cooling rate. Here the cooling rate is 200 degrees centigrade per hour, and it is only 20 degrees centigrade per hour. We are cooling extremely slowly. So what happens in the microstructure? There will be formation of spheroids, and the formation of spheroids increases the machinability. Formation of spheroids increases the machinability. Formation of spheroids increases the machinability. And the diffusion annealing we perform in this range, approximately 1150 degrees centigrade. Diffusion annealing we perform at 1150 degrees centigrade. Now, when we perform diffusion annealing, let us say during the fabrication, you have performed the welding operation at multiple locations. You have performed the welding operations at different locations, and whenever there is a welding bead, it changes the chemistry of the material, because the bead heat affected zone and the parent metal, it's a different composition. So by performing welding operation at multiple location, you have changed the chemistry. So to homogenize the structure, we perform diffusion annealing. We take the material to a high temperature, because in material science there is a thumb rule. That every 20 degrees centigrade increase in temperature, diffusion multiplies by 2. So the foreign element diffuses from one interstitial site to another and make the entire material homogeneous. So diffusion annealing, when we will perform? When we have to make the entire material homogeneous in structure. So I have discussed annealing up to this point. I have discussed. Now, what is the normalizing? What is normalizing? In the normalizing, what we do? We heat the material to a temperature at which austenite is in the stable condition. Whether it's a hypoeutactoid, a hypereutactoid, or eutactoid composition, the temperature will vary. So we heat the material to a temperature at which austenite is in the stable condition. Austenite is in the stable condition. And from that temperature, we quench. Quench in cold air. We quench in cold air. So, quenching in cold air will not produce critical cooling rate. But the surface is going to experience faster cooling rate. Surface is going to experience faster cooling rate, so you will get fine parallite. Microstructure on the surface will be fine. But as we are moving towards center, cooling rates are becoming slower and slower. So you will get coarse grained structure. So towards center, grains will be coarser and coarse. So normalizing produces fine grain at the surface, coarse grain at the center, and fine grains are strong, coarse grains are tough. So these are basically, it's a, you can say one-shot crash course. In the full metallurgy, we will dive deep into the subject and dismantle all these things. So normalizing produces hard surface and tough cores. And these are the microstructure used in final product. So that is the reason normalizing is considered as the final heat treatment process. Normalizing is called final heat treatment process because it produces hard surface and tough cores. That's what we used in any engineering applications. Any engineering application, the material should have hard surface, because hard surface produces resistance to scratch. And tough cores. Why tough core? Resistance to shock. So normalizing is considered as the final heat treatment process. Okay? Final heat treatment product. Okay? Normalizing, hardening, objective of hardening is to produce martensiite. Objective of hardening is to produce martensiite. Objective of hardening is to produce martensiite. But martensites are extremely brittle in nature. Martensites are extremely brittle in nature. So pure martensite, we rarely use in any engineering applications. Pure martensite we rarely use in any engineering applications. What is exactly martensite? If you see the microstructure, what is exactly martensite? It is submicroscopic cementite spread in ferrite structure. Just like a colloidal solution, submicroscopic cementite spread in the ferrite structure. And martensites are extremely brittle in nature. Martensites are extremely brittle in nature. Directly, I cannot use martensite in any engineering application. So, I go for tempering. You know what is the purpose of tempering? Because martensites are extremely brittle in nature. Purpose of tempering is to reduce its brittleness. Purpose of tempering is to reduce its brittleness. So there are 3 types of tempering process. It's the same iron carbon phase diagram. There are 3 types of tempering process. One is called high temperature tempering, approximately at 550 degrees centigrade. So we are heating somewhere in this range. High temperature tempering. Because the temperature is high, so diffusion will be high. So in martensite there is submicroscopic cementite. So submicroscopic cementite will combine together. Submicroscopic cementite will combine together and produces a coarse structure. And the coarse structures are tough. So the result of high temperature tempering is called sorbide. In the sorbide, the cementite is in the macroscopic form, because combining together and producing a coarse structure. Sorbides are tough. Second is a medium temperature tempering. Here the temperature is around 350 to 400 degrees centigrade, meaning here medium temperature tempering. So here because the temperature is low, so the diffusion will also be low. Temperature is low, so diffusion will also be low. So here submicroscopic cementite, again it is combining, producing a little bit coarse structure, but that structure will be finer than sorbide. And this structure is called trustite. This structure is called trustite, sorbide trustite. And third one is a low temperature tempering. and here the temperature is only 250 degrees centigrade. So here is a low temperature tempering. Temperature is only 250 degrees centigrade. So because the temperature is so low that you cannot expect any diffusion to happen at this temperature. Because the temperature is so low that you cannot expect any diffusion to happen at this temperature. And what will happen? Whatever thermal stresses that are generated, those thermal stresses will be relieved. Those thermal stresses will be relieved. That's what will happen. Nothing else will happen. There is not significant change in the microstructure in the low temperature tempering. So you know where we use the pure. So here the resulting microstructure will be martensiite only. Pure martensiite. And where we use such structures? Agricultural tools. Some of your parents will be farmers, because I am also belongs to the village. So you must have seen these things, like the plow that we plow the field. Different tools that we use in agricultural field. That material is a pure martensiite. Pure martensiite. If it breaks, it will break like a biscuit, because it's a pure martensiite. It will break like a biscuit because it's a pure martensiite. So annealing, normalizing, hardening, and tempering. Hardening and tempering. Okay. Upon quenching, austenite, upon quenching will produce martensiite only when percentage carbon is approximately 0.4 to 0.8%. Medium carbon steel range. Meaning low carbon steel is less than 0.3% carbon. Na? Low carbon steel is less than 0.3% carbon. So low carbon steels do not respond to heat treatment process. Low carbon steels do not respond to heat treatment process. Because to produce martensiite, you need a eutectoid composition. To produce martensiite, you need a eutectoid composition. So low carbon steel, there will be too much pro-eutectoid alpha phase. So do not respond to martensiite. Because low carbon steels, we cannot produce martensiite. So what to do? In most of the engineering applications, we use low carbon steels. So in such cases, we use case hardening. Understood? For low carbon steels primarily. Case hardening means, suppose this is the steel sample. So I will change the hardness only of the surface, and I will not touch core. and thickness up to which you have hardened the material is called thickness of case. Thickness of case. So now there are different methods of case hardening. First is carburizing. Carburizing is a process of diffusing carbon into mild steel specimen. So by diffusing carbon, two things are happening. In the surface, composition is approaching the eutectoid composition because we are hiking the percentage of carbon. Na? So if you quench, you will get martensiite. That is one thing. Second is, even if you are not able to get martensiite, carbon is going to the interstitial site. Producing strain field, and these strain fields are creating obstacles in the movement of dislocation, so strength is again increasing. So carbon, by addition of carbon, two things are happening. And we are diffusing carbon, it is called carburizing. Carburizing can be done by three methods. One is called pack carburizing. In pack carburizing, what we do, we take a container, and in the container we seal mild steel specimen along with a carburizing mixture. Carburizing mixture is charcoal, same charcoal that is used in the road construction. Anyway, because it's a crash course, I don't want to tell you so many side things. But generally, when it's a complete course, I will give you a lot of idea basically, so that you become a complete engineer. Charcoal, calcium carbonate, and barium carbonate, and heat at 950 degrees centigrade. In all the carburizing techniques, temperature is approximately 950 degrees centigrade only. So pack carburizing, you seal it, heat it. From the charcoal, carbon diffuses to the mild steel specimen. But pack carburizing is a very slow process. It takes some time, days to complete it. This information is important, whatever I'm writing. That is the reason I have selected for this crash one-shot course. Second is liquid carburizing. It's a dilute sodium cyanide solution, and when we dipped mild steel specimen, it leads to carburizing. See, if it is a concentrated sodium cyanide with different temperature, it leads to cyaniding. But dilute sodium cyanide, I am giving only that much data which is required for you to crack exam this year. That's it. Liquid carburizing produces best quality product. But there is a problem here. Problem here is the bath is very expensive. And highly poisonous. So we have to be careful. Then gas carburizing. In gas carburizing, what we do, we take a container and multiple specimens are packed like this. And at same 950 degrees centigrade, CH4 gas is circulated through it. 950 degrees centigrade, CH4 is gas is circulated through it. So carbon will diffuse into mild steel specimen. So there's a carburizing. Carburizing is a process of diffusing carbon into mild steel specimen. Okay. Now next is nitriding. Nitriding is a process of, see, once again, I am giving you only limited data, but full course I will going to go through in the detail thing. Okay, na? Nitriding is a process of diffusing nitrogen into mild steel specimen. The setup is more or less same. Mild steel specimens. Mild steel specimen. These are mild steel specimen stacked up like this. And in this container, ammonia gas at 650 degrees centigrade is circulated. Ammonia gas at 650 degrees centigrade is circulated. Heat treatment. There is one punchline, and every college teacher asks you to mug up. What is that punchline? Nitriding produces harder and stronger cases as compared to carburizing. Nitriding produces harder and stronger cases as compared to carburizing. The reason is affinity of nitrogen is very large. So when the nitrogen occupies any interstitial site, it produces a strain field of larger intensity. It produces a strain field of larger intensity. So nitride cases will be very brittle. So after nitriding generally, further heat treatments are encouraged. After nitriding, further heat treatments are encouraged because my surface is too brittle. Okay. Third one is cyaniding. Cyaniding is the same concentrated sodium cyanide bath. And here is a mild steel specimen, and the temperature here is 850 degrees centigrade. See, carburizing it was 950, nitriding it is 650, and cyaniding it is 850. Cyaniding it is 850. Okay, na? There is something called carbonitriding. Carbonitriding is also called gas cyaniding. It's the same setup, and the temperature is 850 degrees centigrade. I told you cyaniding temperature, whether it's a gas cyaniding or cyaniding, temperature remains same. So both carbon and nitrogen gases, CH4 and ammonia, both are circulated through it. So both carbon and nitrogen will be diffused into the mild steel specimen. One thing you should mug up, nitriding produces hardest cases, then carburizing. Cyaniding will always be in between. The temperature here is 950, this is 850, and this is 650. Because it's a one-shot crash. That's the reason I'm repeating certain things, means that point is very important. If I'm repeating certain things, it means that point is very important. carburizing, nitriding, cyaniding, gas cyaniding, or carbonitriding. Now, there is something called induction hardening. Induction hardening. Induction hardening is also a case hardening technique. Induction hardening is also a case hardening technique, but it is meant for only alloy steels. It is not meant for low carbon steels. It is meant for alloy steels. Crankshafts, connecting rods are case hardened by this technique. Okay, na? So the system is, there is an induction coil, and on this side of the induction coil there is an oil bath. There is an oil bath. On the other side of the induction coil there is an oil bath. Now specimens are passed through induction coil. Specimens are passed through induction coil. So the way it works is, induction coil will produce eddy currents. Suppose this is the specimen. Eddy currents will be formed only in the surface. Eddy currents will form only in the surface. The electrical principle is, wherever eddy currents are formed, heat will develop. Wherever eddy currents are formed, heat will develop, and the heat will be highly localized. So once the heat is developed, it is quenched into oil bath. So you will get a very thin layer of martensiite. And this thickness X is equals to 5000 under root rho by mu F. F is the frequency of operation. Mu is the magnetic permeability, and rho is the electrical resistivity. So the thickness of case thickness I can change by changing the frequency. Induction hardening is the fastest way of case hardening the specimen. Once again, we are touching only the important things. Flame hardening. Flame hardening is meant only for medium carbon steels. See, carburizing, nitriding, cyaniding, gas cyaniding are meant for low carbon steel. Induction hardening for alloy steel. Flame hardening for medium carbon steel. So the way we do it here, suppose this is the work, and there is one rod. Here there is a flame, and here there is a jet, water spray, and here we take the oxidized flames. Why we take the oxidized flames? Same gas welding, oxidized flames. Why we take? Because oxidized flames are hottest. Why we take? Because oxidized flames are hottest. That's the reason we take it. So by heating the work, simultaneously it is quenched. So you will get a thin layer of martensite over the surface of work. Popularly, the flame hardening is used to case harden machine beds. Flame hardening is a technique that is used to case harden the machine bed. So now what we have discussed different heat treatment processes, and now I have certain questions, and to handle the questions, whatever is required for handling the question, whatever is required, I will explain. Okay, whatever is required to handle questions, I will explain. Okay, please read the question. It's a MSQ multiple select question. It's a multiple select question. Okay, so I will follow the same approach. I will pause for 30 seconds so that you can process. Which are the sources of internal residual stresses in the metal components? Plastic deformation. Plastic deformation leads to dislocation pileup. Dislocation pileup. Plastic deformation leads to dislocation pileup, and there will be internal residual stresses. Non-uniform cooling of a workpiece, as I told you, during quenching, there will be thermal stresses, and thermal stresses are basically the internal stresses. It's a correct statement. Phase transformation. During the transformation of one phase to another phase, the phase boundary, there will be stresses. So ABC, it's a multiple select question. ABC, multiple select question, ABC. Now match the following. Match the following. I will give you some time to process. I will give you some time to process. So TTT diagram, coarse parallite you will get here, and when we will get coarse parallite? When the cooling rates are very slow. And where out of these four, very slow cooling rates are possible only in the furnace. So D has to be 4. So B and C cannot be the option. So these things we do by the process of elimination. Okay, Martensites. Oil and air cannot produce the critical cooling rate. Oil and air cannot produce the critical cooling rate. Either generally the brine solution will produce, because in water there will be tendency of the vapor blanket formation. Brine solution means if you add 35% salt, tendency of vapor formation will reduce. So best is the brine solution, but it is not here. So Martensites with B will water. So A is to 1. Answer is first, or A. Very fine parallite we will get oil, fine parallite air, because cooling rate of oil will be less than air. So very fine parallite we will get in oil. So that is the way we should handle such type of problems. That is the way we should handle such type of problems. Okay. Yeah. Question number 3. there is something called age hardening. Age hardening. You know how the age hardening concept came into picture? How the age hardening concept came into picture? There was one scientist, Professor 𝐂𝐴. So he was conducting an experiment in his laboratory. Why I am telling a story? Because with the help of a story, you grasp in a better way. In the regular course, I am going to teach many stories linked with the concepts. So when the Professor Hume was conducting experiments, it was a well-established fact that for iron upon quenching, strength can be increased because it's a martensiite. So what Professor Hume thought, aluminum is another very important material. The problem with the aluminum is that it is not strong. So if I can increase the strength of this material, so what he did, he was alloying aluminum with different materials, taking to a certain temperature and quenching with different rate. After quenching, he was measuring hardness. Nothing was happening to the material, and almost 1 year passed for doing these experiments. Almost 1 year passed. So one day he became angry. He took the 2 specimens and thrown out of the window. He took the 2 specimens and thrown out of the window. And after that, fortunately, it was Christmas holiday. In foreign countries, India Christmas holiday is only 2 days, na? In foreign countries, it is a major holiday, 1.5 months. People will go on 20th December, they will come in first week of February. So it was a long holiday. So after almost 1.5 months, Professor Hume came to laboratory. So he thought that maybe I was angry that day. I have not measured the strength of samples lying outside. So he jumped out of the window, collected the specimens and measured the strength. Those specimens were stronger. So he said, Eureka, I got that funda. Because he was having all the data, he took exactly the same composition, taken the sample to exactly the same temperature, quenched with the same rate, and then measured the hardness. Nothing happened. So then idea clicked to his mind that maybe it is the time factor that is doing something. And then he invented the concept called age hardening. And by the way, it was aluminum copper alloy, and that's where duralumin was invented. Duralumin. Aluminum copper alloy is called duralumin. What is exactly happening in the material? That after quenching, copper is freezing at its location. And as the time passes, copper is coming out of the microstructure. And form precipitates of Al2Cu. These precipitates creates obstacles in the movement of dislocation. And any activity that creates obstacles in the moment of dislocation will increase the strength. And this phenomena is called precipitation hardening or edge hardening, and it is meant for non-ferrous materials, especially aluminum alloy. It is meant for non-ferrous materials and especially aluminum alloy. So aluminum, this magnesium is also very, very important material. Lot of aerospace components are produced by aluminum alloy. Magnesium is very important material. It is used in biomedical applications. Magnesium is used in the biomedical application. So biomedical, there are two very, very important materials. Another one is the titanium, second is the magnesium. Why magnesium? Because its density is very low. So a lot of screws are manufactured out of magnesium. And why we use titanium? Why we use titanium? Because its Young modulus is very close to our bones. Young's modulus is very close to our bones. So titanium and magnesium are the number one choice. We don't use steel anymore. Like for example, there is an accident. The bone is broken. We have to put rod and all these things. All the implants, body implants are either titanium or magnesium. It is no more steel. So anyway, I have extended the solution because certain portions I am not covering in this series, one short series. Otherwise, purpose will be lost. Purpose is, in a short time, whatever is the important section, we should be in a position to deliver you. That is the idea. Okay. Yeah. Fourth question. I will give you time to process. I will give you time to process. I will give you time to process, please. After that, we will verify. After that, we will verify. During heat treatment of steel, the hardness structures in order is martensite is the hardest. Martensite is the hardest. Material science, you remember another thumb rule. Material properties like strength, hardness, brittleness, primarily it depends upon the crystal structure. Primarily it depends upon the crystal structure. When the crystal structure is same, now it depends upon the grain size. Grain size is the culprit now. And spheroidite will be the most ductile. Spheroids annealing, because spheroids are most ductile. Hardest, see, fine and coarse perlite. This will be more ductile, this will be less ductile. Strength will be more here. Strength more here, because fine grains are more stronger than the coarse grain structure. I have 3 lectures, YouTube lecture on dislocation theory. You just type my name, 𝐂𝐨𝐿, dislocation theory. There you will get my 3 lectures. So you can see all these things there. So option A is correct. Option A is correct. Yeah. Next question. Match the list 1 and list 2. Ductile iron, white cast iron, malleable iron, rail joints. Rail joints is thermit welding, but it is present in all the options. So nothing is cancelled. Anyway, this is annealing. This is annealing. Malleable iron we will get by annealing only. White cast iron by chilled iron. Ductile iron by inoculation. Answer is 1. So I will give you some name because one shot I have not discussed these things. There are different types of cast irons. When the percentage of carbon is more, this carbon will appear in the free form in the material, and such cast irons are called gray cast iron. So when the carbon is present in the free form, it is called gray cast iron. But when you heat it, so that everything will convert into liquid. From the liquid state, if you rapidly cool it, so carbon will think, I should be inside or outside. Before carbon can take this decision, temperature is the room temperature. So technically carbon should be outside, but it locked inside. Such cast irons are called chilled cast iron. There is one very beautiful book of material science, I do not recommend. He gives this very wonderful definition. Cast iron of such composition in which it will normally freeze as gray, but by rapid cooling forced to appear as white is called chilled cast iron. Abner is a very beautiful book, but I don't recommend. Okay, na? For competitive examination, your study should be selective. So answer is A. Yeah. The formula we studied. About the induction hardening. Thickness of case is in the induction hardening process, it is high. It is high frequency, because primarily I am tinkering with frequency only. If the frequency is not high, then X will be high, na? So my eddy currents will penetrate into the thickness that I don't want. So it should be high frequency so that I can maintain the thickness of toughened case, thickness of hardened case. Correct, na? It's okay. Easy one. Read it. Because if all the questions, if I give the answers immediately, what is the fun? Diffusion coefficient in carbon through iron during the hardening process. Read it. Although, of course, you will be seeing the recording, but I want the things should be taken properly. Okay, what I told you, then material science, there is a thumb rule that every 20 degrees centigrade increase in temperature, diffusion multiplies by 2. Technically speaking, it's an exponential curve. So increases with the temperature. Diffusion always increases with the temperature. It's the same thing. I given you the story of age or precipitation hardening. Look at it. Precipitation hardening is a strengthening method for steels and alloys, which is also called as age hardening. It's the same thing. We have discussed a lot. about this. Read the problem. Liquid carbonate trading. Process of case hardening is also called as liquid carbonate trading is a process of diffusing both carbon and nitrogen called cyaniding. Once again, cyaniding produces best quality cases, but there are only two problems. First problem is it is expensive, and the second problem is it is highly poisonous. Suppose worker dies, it is a responsibility of the company. If the worker dies within the four walls of company, it's the responsibility of company. It's risky. Yeah, 10th question. A little tricky. I will wait for 30 seconds. A little tricky. I will wait for 30 seconds. Okay. Consider the following statements. The quenching of steel results in an increase in wear resistance, strength, and hardness. It is correct, because resulting microstructure is martensiite. Resulting microstructure is martensiite, so wear resistance will also increase and strength hardness will also increase, because that is a characteristic of martensiite. 2. By the process of case hardening, hard wearing resistant surface is produced on mild steel. Mild steel is also called low carbon steel. I hope this much material science your BTech people might have taught you. Once again, if you have any query, please join the PW Telegram channel and direct all the queries to me. Okay. This is an effective method for low carbon steels because they cannot be hardened by the process of quenching. Correct statement. Very correct. So 1 and 2 are correct. Oh, still there are two options. Okay, third we will read. When a metal is mixed with small atoms of non-metallic elements in such a manner that invading atoms occupy interstitial positions in the metal lattice and interstitial error results. I told you in this one-shot course also, when you add, there are two options. One is a compound, another is alloy. It is asking about the alloy. So when you add impurity atom, again there are two options. Impurity atom occupies the interstitial site like carbon and nitrogen, or impurity atom may occupy the substitutional site like manganese, magnesium and all that. I am talking about iron. So third statement is also correct. Answer will be D for Delhi. Answer will be D for Delhi. I hope, because if it's a live class, it would have been different mechanics. Okay, but because this year, you can take it as a revision course also. You can take this as a revision course also. Read it. I will wait for 30 seconds. Read it, please. On completion of heat treatment, the austenite structure would be retained. It is called gamma rat. When the austenite structure will be retained, see, suppose the martensiite finish line is greater than room temperature. Martensiite finish line is greater than room temperature. When we quench, it will be 100% martensiite. That's what we studied. But suppose Martensite finish line is less than room temperature. After quenching, the point will be above MF line. Here will be retained. Gamma rat will appear like this. Here it will be retained. So now which option is correct? C? D? Check the diagram. Whether D is okay or no. Check the diagram, please. Check the diagram, please. Retained structure. This is also a very beautiful question. This is also a very beautiful question. A steel is hardened and heated about 875 degrees centigrade. Where the structure consists of entirely austenite. It is then cooled suddenly at a temperature of 250 to 520 degrees centigrade. This is 550 and this is the 220. So it is quenched in this range. It is saying, the question is saying in this range. This process of heat treatment is known as austempering. This process of heat treatment is called austempering. Okay. This is the last question from the heat treatment. Last question from the heat treatment. Ductile to brittle transition temperature. You know, there is something called equicohesion temperature. There is something called equicohesion temperature, like a Titanic tragedy. How it happened? Because the hull material equicohesion temperature was 0 degrees centigrade. Below equicohesion temperature, ductile material will transform into brittle material. So it will flail like a chalk piece. So when the iceberg hit, it was a brittle fracture and the ship was divided into two parts. So this equicohesion temperature depends upon the size and shape of material, rate of loading, presence of notches, impurities, and operating temperature. So of course I have basically not thoroughly gone through it, because the purpose of this course was, in short, in English, whatever is required for GATE 2023, we can give in a capsule. So I have tried to discuss primarily the phase diagrams and the heat treatment, because in GATE, especially for this year, I'm thinking the question may come from this section only. So that was the one-shot course of material science. I will be taking metal forming, metallurgy, and casting. So if you are attending only this lecture, I wish you all the best. Otherwise, join other courses also, like for example, metal forming, metallurgy, and casting. So thank you very much. That's it.